Okay, troops. Central force is the name of the unbalanced force that's required to keep an object moving in a circle with a constant tangential speed. Now we know from further down the school, from fourth year and from last year, that an unbalanced force causes a mass to accelerate. And last time we were talking about the fact that an object that's moving in a circle has a radial acceleration. That radial acceleration is given by A equals v squared over r. So if we just substitute that into Newton's second law, we get F equals mv squared over r. One of the most important equations that you're going to meet this year, not just in this unit, but in subsequent units as well. Now, again, we can substitute in for tangential speed and angular velocity to get a different form of the equation. So since tangential speed equals your angular velocity times your radius, we can substitute in for v in this equation with omega r, and therefore it will become m omega squared r squared, and one of the r's cancels and we end up with m omega squared r. You might also see it written as F equals mr omega squared, but bear in mind both of those relationships are on your relationship sheet. The central force equation, the force that's required to keep an object moving in a circle. Now we're going to do a wee experiment, right? Before we do that though, we're going to mention two words, one of which we will use and one of them which we should not use. Centripetal force is the name that's given to the force that keeps an object moving in a circle. Centripetal means centre-seeking force. On the other hand, centrifugal force is a fictitious force. It's not real. It is what you feel when you're moving in a circle. If you're in a car and you're going around a corner, you feel as if you're being thrown out of the circle, when in fact all that's happening is your body's trying to continue at steady speed in a straight line and obey Newton's first law. And what you actually feel is just the reaction to the centripetal force that's keeping you moving in a circle. You being thrown out of a circular path is only you obeying Newton's first law. Right, here's our two central force or centripetal force equations, both on the relationship sheet. And what you will notice about both of them is that the force required to keep an object moving in a circle varies directly with the tangential speed squared. So if the mass and the radius are constant, F varies directly with v squared. Or over here, if the mass and the radius are kept constant, and if F varies directly with the angular velocity squared. What we want to do is a little demonstration or a wee experiment to verify that experimentally, that relationship between the centripetal force and the tangential speed, or centripetal force and the angular velocity. So here's the experiment, the relationship between centripetal force and angular velocity. So similar apparatus that we used to describe circular motion in the first place and radial acceleration. It's a rubber stopper and it's going to be moved in a circle, and that central force is going to be supplied by the weight of a hanging mass. We're going to vary the weight of that hanging mass and measure the corresponding angular velocity. So here's the instructions. We're going to start off with a 200 gram mass on the string. We've got our little marker on the string so that the radius is going to be kept constant at 0.6 meters. we're going to swing the rubber stopper in a circle until this mass is being held stationary with the marker in the correct location. When it's in this state, the central force is being provided by the weight of the hanging mass. And then what we're going to do is, if we know what the central force is, we just calculate the weight, W equals mg, so for a 200 gram mass that will be 1.96 newtons. For each weight we're going to measure the angular velocity. We'll do that by timing how long it takes for 10 revolutions. 10 revolutions is 20 pi radians, 2 pi radians in a revolution. And we will time 10 revolutions. From that we can work out the angular velocity in radians per second. The angular velocity will be 20 pi divided by the time for 10 revolutions. And if we repeat that with 400, 600, 800 grams and then with 1 kilogram, we can plot a graph of the centripetal force against the angular velocity squared. Why are we plotting F against omega squared? Because in both of our relationships, the centripetal force varies directly with either the tangential speed squared or the angular velocity squared. Let's see how we got on. Now you may need a table of results that looks like this. Then we'll do the experiment, get it filled in, have a go at plotting the graph, then I'll come back and I'll show you mine. Right, central force. Central force is the force that is required to keep a mass moving in a circle. It's the force, the unbalanced force that's required to give that mass a radial acceleration directed towards the centre of the circle. Now, I'm going to do a wee experiment using a rubber stopper, which I'm going to whirl around my head. To keep that moving in a circle, we need a central force. That central force is going to be provided by various masses, 200 grams, 400 grams, 600 grams, 800 grams and a kilogram. And we are going to time how long it takes for 10 revolutions of this bung around my head when the central force is applied by hanging various masses on here. So I'm going to start off with 200 grams. There it is, 200 grams. I'm going to hang that on the bottom and then whirl it around my head. Now, I put a blue mark on it the other day. There's that blue mark. The reason for that blue mark is so that if I am swinging that round my head, okay, then as long as I can see that blue mark and I go at a certain rate or at a certain speed, if that blue mark is stationary, then I know that that mass is moving in a circle with a radius of 0.6 metres. The force keeping it moving in a circle is due to that mass of 200 grams. It's 1.96 newtons. And what I'm going to do is I'm going to time how long it takes for 10 revolutions. Then I'm going to repeat that with 400, 600, 800 and 1 kilogram of mass. So, here we go, I've got the 200. Need my stop clock. Go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the time. There we go, 8.12 seconds. Okay, now I'm going to repeat it with 400 grams on there, so the central force will be the weight of that 400 gram mass, so 0.4 times 9.8, This time I can already feel it. I'm going to have to spin this faster to support that weight. In other words, we need a bigger central force to keep this mass moving at this increased rate. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. That's the time. 5.76 seconds. Okay, next one. 600 grams. 0.6 times 9.8 will give us the central force. I'm needing to go faster again this time. Here we go. It's balanced. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. 4.72 seconds. Next one. 800 grams. Blimey. I need to swirl this one right fast now. Let's go. There's my blue mark. There it is. Okay. Right. Here we go. Ready? 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. 4.08. Okay, and the last one, 1 kilogram. 9.8 newtons. Yeah. Oh, blimey. Get it balanced first. Oh man. Here we go. 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop. I hit myself in the head there. 3.65 seconds. Now, what we're going to do with these results is we're going to put them on the table and then plot a graph of force on the x-axis against angular velocity squared on the y-axis. And let's see what we get. Right, once you've done the experiment, here is the sort of table that you will have for your results. And once you put those results in the table, we'll be able to plot the graph. Remember, the central force is just the weight of the mass. Time for 10 revolutions from your stop clock. And you can work out omega from that. Omega equals 20 pi over that time. And then square your omegas. Are you ready for my results? Right, here are my results. There's the central force. It's just the weight of the mass in each case, W equals mg for each of them. There's the time for 10 revolutions for each of those masses. Then worked out omega. Omega was 20 pi over t, because it was 10 revolutions, 2 pi radians per revolution. We then squared omega to get omega squared. Now, we have not done any uncertainties because we just want to go through this quite quickly. If time had permitted, we would have worked out the uncertainty in the central force and the uncertainty in the time. We would have repeated it as well 5 times, worked out the random uncertainty in the mean. We would have worked out the uncertainty in omega and then doubled it to get the uncertainty in omega squared. So, here is my graph within the limitations of the experimental uncertainties. So, there it is. It's a straight line. It's a linear relationship between the central force and angular velocity squared, and it is almost a direct relationship. We've got a very slight systematic uncertainty here. Y-intercept of minus 0.9. But it's pretty good. So within our limits of experimental uncertainties, we can consider this at the moment to be a direct relationship between f and omega squared. The gradient of the graph is 30. Let's analyse that. So, f varies directly with omega squared, and the gradient of our line is 30. If we think about that gradient a wee bit further, because y over x was omega squared over f, if we flip that whole thing upside down and get f over omega squared is 1 over 30, by looking at the relationship, if f over omega squared is 1 over 30, then mr equals 1 over 30. Just rearrange the equation. And since the radius was 0.6, we can substitute in for r for 0.6 and work out what m is, what the mass of the rubber stopper was. Works out to be 56 grams from our experiment, and when measured on an electronic balance, I got 55 grams. So that's not bad. Quite a nice little experiment that demonstrates the relationship, and then some further analysis we could do to work out the mass of the object that was moving in a circle. Anyway, let's move on. Let's try some examples.